Okay, so we got our work energy theorem, okay, problem here. And the first thing we want to do with all problems is obviously write out our givens. 200 grams. What is that? Mass. What does it need to be in? Kilograms. These are just the little details we always have to watch for. Questions are trying to trick us. Just be paranoid. They're always trying to trick you. Okay? So, I've got a mass of 0.2 kilograms, and it's launched from ground level. What's the height if you're on the ground? Right. Okay. And it reaches a height of 1,600 meters, so that would be our final height. How much work is done? Okay, so there's my first bit. I've done the givens part. The second part of this is to write out work energy theorem. Work is a change in mechanical energy, but in this case, it's only a change in potential energy. How do we know that?
Does it mention its height?
Right, the height's changing. It doesn't mention anything about the speed, although, I mean, it's a rocket. The speed is also changing, but we're not dealing with that part of it. Okay, so we're just dealing with the potential energy part, so in this case, work is changing the potential energy. Okay, was I given force and distance? I was given distance, right, good, some of you remember that from the other day. Okay, if we're looking at a change in potential energy, the distance over which the force acts is the same as the distance or the change in height, okay, because that's where we're working at. So we do know the distance, it's also 1,600 meters. All right, but I don't have the force, so I can't calculate work using force times distance in this question. But I can use the change in potential energy to get it, because I have enough information to do that. So that'll be potential energy final minus potential energy initial. Since I was on the ground, what's EPI? 0. Okay, so I can get rid of that. That saves me time. So I'm left with this. Work equals M times G times H final. Okay. So all I have to do is plug in my numbers. That'll be 0.2 kilograms times 9.81 times the final height, 1,600 meters. Okay, and so we should get, hang on, I forgot to fire up my calculator. Okay, 0.2 times 9.81 times 1,600. Okay, so we are looking at 3,139.2 joules worth of work being done. Okay, so that would be all we have to do for part A. For part B, they want to know how much force the engine exerts. Well, now that I have the work and I have the distance, now I have enough information to calculate the force. Right? So all I have to do is divide both sides by D. Okay, and that'll leave me with force. So I take my newly calculated number here, 3139.2 joules, and I divide it by 1,600 meters. Right, which tells me 1.962 newtons worth of force was required. Okay, always be careful of your units. It's really easy to get units for force and work confused. Newtons are for force and joules are for work and energy. Okay, now the other thing that you may notice or maybe didn't notice, and it's okay if you didn't because this is a perfectly valid way to solve this problem. But when we set this up, force times distance, and we go M times G times H, okay? If I divide both sides by D, remember that D and H were the same number? What do they do to each other? They cancel. So I could also calculate the force by multiplying M times G. Okay? Because whenever we're changing the potential energy of something, we only have to exert enough force to overcome the force of gravity. And on your formula sheet, I believe, you will see this formula, that the force of gravity is mass times gravity. That's the thing we were telling you about the other day where, if I'm, somewhere and somebody asks me how much I weigh, I tell them exactly how much I weigh, 785 newtons. Okay? Because it's really rude for them to ask me that question, so I feel like making an example of them and giving them a truthful answer that they don't understand. Okay? Because they didn't want my weight, they wanted my mass. But they don't know that. And they obviously don't know it's not polite to ask people how much they weigh. So, I get to teach them 2 lessons at once, and I'm all about teaching. It's my life's work. Okay? So, that's the other way you could have done that. Probably most of us just did it this way, and that's perfectly bad. Okay. All right. I have been looking at the need for speed labs, and I am deeply troubled because the calculations for displacement are, well, on at least the first few that I looked at, wrong. And not just a little bit wrong, really, really wrong. And I'm not, when I say this, guys, I'm not trying to belittle anybody, but you use this ramp for the lab. How long is this ramp? It's probably a little bit more than a meter. Why don't we get a measuring device out and we'll figure it out. So what I'm trying to do here, guys, is get you to think about your answers when you calculate them. So there's 1 meter. These are 1.2 meters long. So when you calculate the displacement and you get that the cart, while accelerating down this ramp, traveled 10 meters, should you question that number? Yes. Okay? Like if something doesn't make sense, question why. Okay? My concern is that people didn't realize that that answer didn't make sense. I think people were just like, oh, thank God I'm done doing this calculating. I hate math, and I just want to be done, and I've checked that box now. Okay? And that concerns me a bit, because I want you to understand how things work and why they work. Because on a test, if I ask you to calculate something, I want you to look at an answer and go, yeah, that answer makes sense. I think that's right. Versus, oh my God, why is it saying that I weigh 55,000 newtons in this answer? That can't possibly be right. I must have done something wrong, and I better double check what I did. Okay? I want you guys to be able to do that. I want you to be able to look at an answer and evaluate it. Okay? Not go, okay, good, I'm done. Okay? So I just want to take a quick look at some data here. And I think this is the data that I got, but I used a slightly longer ramp. I think I used the 2.5 meter ramp when I did this, but we'll see in a minute. When we want to calculate the displacement of an object from a velocity versus time graph, and I need everybody paying attention here, please. Okay? Let's say we're looking at the blue line for right now. Okay? If I want to calculate the displacement of the object, I need average velocity, okay, and I need time. I spelled that wrong, average, okay, and I need time. Well, time I can get off the x-axis. According to this graph, all of those things stop at 1.25 seconds, okay? The average velocity, I have to actually get in 2 ways because there's kind of 2 parts to this motion, okay? The carts are accelerating, but they don't accelerate, well, they do accelerate the entire time, but they don't start at 0, at least according to the line they don't. So that means I have to figure out how far they would travel if they traveled at their initial velocity. That would be this rectangle here on the bottom. And then how far did they travel while they were accelerating? That would be the triangle above it. Okay? But in both cases, I'm going to use average velocity times time. I'm just going to get that average velocity differently. Okay, so this is how this needed to look on your lab. For the blue line, does it tell me how tall that rectangle is? Yes, it does. Okay, the equation of the line tells me that the y-intercept, that is, what's the y value at time 0, is 0.319 meters per second. By the way, that was another place. In the chart where you were telling me what slope was and what b was, the units were kind of a mess. Okay, is b on the y-axis? It is. So does it have the same units as the y-axis? It does. Okay, so your units for b should have been meters per second. It's your initial velocity. It's how fast the object was going at time 0, so it should have been in meters per second. Okay, and your slope should have been meters per second squared because it represents the acceleration. Okay, and your displacement should have obviously been in meters. All right, so looking at this box here, okay, I know the height of it is 0.319 meters per second, and the base of it is 1.25 seconds. So I can calculate the area of this by going average velocity, which will be 0.319 meters per second, okay, times time. So 0.319 times 1.25 seconds. So 0.39875. meters. Okay, that's the first part. Now I've got to calculate the area of my triangle. Now, I don't know what the height of my triangle is because I don't know what y is at 1.25 seconds. But can I figure it out? How would I figure it out? How can I figure out a y value if I know x is 1.25 seconds? Use the equation. That's what the equation calculates for. Remember, this is y equals 0.612 times x plus 0.319. And I can read what x is right off the graph. It's 1.25 seconds. So I'm going to figure out what my y value is right here by simply going 0.612 times 1.25. Okay? And I'm not going to add on the 0.319. Why not? I saw you added it on and subtracted it off after.
Yeah, because you didn't, that'd be accounting for the, like, getting it to 0, but you're trying to, like, it's where it started. You don't want, like, it's acting like it's at 0 if you add that, or if you don't add that.
Yes, absolutely right. I only want the height of the triangle. I don't want the height from the x-axis. I only want this part. And that's where a lot of people went wrong. They used the full height of this, which is a much bigger triangle. Okay, does everyone follow me there? It's a much, much bigger triangle. So I only want this part. That's what this will calculate for me. So that part's 0.765. Okay, now that I know the height of my triangle, I can calculate the area of my triangle. And that's still going to be average velocity times time, because it's going to increase in velocity from this value to this value, which means its average is right smack in the middle, which is why I always divide the height of a triangle by 2 when I calculate its area. That's going to get me the average velocity during the part of the motion where its velocity changed. Okay, so I'm just going to go base times height over 2, and that will give me time multiplied by average velocity, same as it was for the bottom. So the base is 1.25 times our 0.765 divided by 2. All right, 0.478125. Okay, so now I've got the two displacements. What do I do with them? Add them together. Okay, so you know what? This was for the short ramp. Okay, so I'm going to take that number and add it to that number. 0.877 meters. That's pretty reasonable, because if I was using this ramp, I couldn't use the first part here because of this piece of meter stick that we used to put pulleys on, okay? And I probably stopped it before it got to the bottom. So, you know, yeah, that's about right. That's about where we stopped. And plus, you gotta imagine that the cart is this long. So, holy smoke, it's almost perfect. It's 90 centimeters from where I would set the cart to the end of the ramp. Okay, and remember, I didn't let the cart go off the ramp, I stopped it here. Okay, so center of the cart to where my hand is, according to this line, about 91 centimeters. Now that's got to account for reaction time and some of the stuff we cut off in our data. That's a perfect answer for this ramp. Okay, it makes sense for this ramp. And that's the process I want you to go through. Okay, when you're getting an answer, don't just go, oh, thank God I'm done. Okay, look at your answer and go, okay, what was I doing when I collected this data? Does this answer make sense given what I did? Okay, that answer makes sense for this ramp. It makes perfect sense for this ramp. Okay, everybody all right with that?
I just have, like, was this on your podcast that you had in the lab? Because I remember watching it, like, we, Sapphire and I were trying to watch it the whole time, and, like, maybe a key part that, like, somebody said in class, I could not hear anything, so we had to just, like.
Okay, but I was here. I did say this in class on the day we did the lab, and I was here for help. I didn't have too many people come in and have their labs checked over or ask any questions about them. So even if it wasn't in the recording, it was certainly something I did cover in class on the day we did the lab. Yeah, because I used an old recording.
Yeah, that's what,
Okay? But I mean, we've done a lot of like graphs, velocity versus time graphs, where we found the area. This is no different than any of the other ones we've done. It's always the area of the shapes. Find the area of the shapes. Okay? People just went wrong on the area of the shapes, and some very, very much so. Right? At least from what I've seen so far. Maybe it was just the first ones I picked, and I got really bad luck, and everybody else's are great after that. I hope so. Okay? I just want to address it because, well, I printed your unit exams, and this is on it. So I really want to make sure you know what you're doing with being able to calculate displacement from a velocity time graph. Okay? Does that make sense to everybody? I'll go over this whole thing tomorrow when I go over your labs in full, but that's a pattern I saw already and only having looked at about 7 or 8. Okay. All right. Well, let's go back to work energy theorem here. Okay. I want you to write this one down and give it a try. Right, so we got a rubber band used to shoot a marble along a level floor. Notice it's not at anyone, okay? Along a level floor. The rubber band is stretched using 300 newtons, and the marble starts from rest and reaches a speed of 18 meters per second. How far was the rubber band stretched? Okay, so another work energy theorem problem. I'll give you a few minutes to try that, okay, and then we'll go through it. Okay, let's go over this one. So we have a rubber band that's used to shoot a 0.135 kilogram marble. So they just gave us mass, 0.135 kilograms, along a level floor. Okay, as soon as they say it's level, what's not changing? Height. Okay, so what kind of energy is changing here? Kinetic, okay? Plus they tell me that it changes from rest to 18, so okay, that's kind of a dead giveaway as well. All right, we know the force used is 300 newtons, okay? And we know that it starts from an initial velocity or initial speed of 0 meters per second to a final speed of 18 meters per second, okay? That's the information that we were given. We are trying to find the distance over which the force is exerted, how far the rubber band is stretched. So, as we said just a minute ago, in this question, it's the kinetic energy that's being changed by the work, okay? Because it's making the marble go faster. So, we've got to expand this out to force times distance equals, okay, EK final minus EK initial. What's my initial kinetic energy? 0, starts from rest, so I don't even need to have that part on there right now. So then I can expand to this. FD equals 1/2 mass times speed final squared. Right? I have all of those numbers except for d. So how do I get d by itself? What do I have to do to get d by itself? Divide by force. Okay, so I'm going to divide this side by force, and according to the rules of algebra, I've got to do that to the other side as well. So now I've got my formula. D equals, okay, 1/2 times 0.135, the mass of the marble, times 18 squared, the final speed of the marble, divided by the force, 300 newtons. So I'm going to put the units in that part. Okay, so when I punch this into my calculator, everything's being multiplied and divided, so I don't have to worry too much about brackets. 0.5 times 0.135 times 18 squared divided by 300. Okay, well, they didn't stretch it very far. That's 7.29 centimeters. That's far enough. I mean, that's so far. We stretched the rubber bands yesterday in our work lab. Okay, so our answer will be 0.0729 meters. Okay, did you make note of what I did just there when I got that answer? What did I do? I saw a really small number and immediately questioned it. I went, ooh, that seems kind of small. Then I went back to the context of the question. This is a rubber band being used to shoot a marble. How far can I stretch a rubber band? Well, yesterday we stretched a rubber band about 12 centimeters. Yep, that makes sense. Okay, I checked my answer to see whether it fit within the bounds of our reality. Okay, now the bounds of my reality say that's a reasonable amount to stretch a rubber band. Hopefully yours do too. Okay, I mean, obviously all rubber bands are different. If I had a big long bungee cord, which is just a big rubber band, I could probably stretch it further than that. But this was a small rubber band shooting a marble. 7 centimeters makes sense as an answer. Okay? And I always do my best to make sure that answers make sense. If they don't, I'll say it and I'll own it and go, hey, I made that one up on the fly and that's why that answer doesn't make sense. And sometimes that happens. It'll never happen on a test. Okay? On a test, your answers should make sense within the bounds of reality. All right, any questions on that one? Okay. All right, try that one. So we got a sprinter who is exerting 225 newtons worth of force. Over the last 10 meters of their race, they increase their speed from 14 meters per second to their maximum speed. What is their maximum speed? So this one, the algebra is a little bit more involved, okay? You don't have any values that are 0 in this question. Okay, let's go over this one. Now, to be completely transparent, this is probably about as hard as a work energy theorem question would get for you in terms of the algebra, okay? Because you have to do a bit of extra manipulation on this. It's not like super challenging, but it's probably the most challenging of the ones that we would get. Okay, so first thing we want to do is write down our givens. We know the mass of the sprinter to be 75 kilograms. We know the force they can exert is 225 newtons. Okay, we know that the distance over which they exert that 225 newtons worth of force is the last 10 meters of the race. Okay, we know that they increase their speed from an initial value of 14 meters per second to their maximum speed. And we're supposed to calculate their maximum speed. All right, so what kind of energy is being changed in this question? Kinetic or potential? Kinetic. The speed's changing. If speed's changing, it's kinetic energy. If height's changing, it's potential energy. That's just something we got to know. Okay? So this is a change in kinetic energy. So now I'm going to expand this out a little bit. I have both the force and the distance, so they're likely that I'm going to have to use them. Okay? And I know that I'm changing the kinetic energy, so that's going to be kinetic energy final minus kinetic energy initial. Now, before I expand out any further, okay, which one of those terms is VF going to be part of? EKF. It's part of the runner's final kinetic energy. So I need to isolate this before I expand it out. Sometimes it's easier to subtract it when it's one term as opposed to a whole bunch of variables. Okay, so what do I have to do to get EK by itself? What do I have to do with EK initial? Add it, yeah, okay, do the opposite. So I'm going to have force times distance plus the initial kinetic energy equals the final kinetic energy. Now, again, here's one of these things you can talk through as you're doing a question to see if you're on the right track. What's the definition of work? A transfer or a change in energy. Okay, so if I take the work, which is a change in energy, and I add it to my initial kinetic energy, that should allow me to arrive at my final kinetic energy. Agreed? So far, my manipulation and my algebra makes sense. Okay, so next thing I want to do is expand these two out so I can see all the variables. So that'll be force times distance plus 1/2 mv initial squared equals 1/2 mv final squared. I'm looking for this. So what do I have to do with the half and the m? Divide them over to the other side, because right now they're all being multiplied. So we want to do the opposite. So we'll divide that side by half of m, and then we'll divide this side by half of m. Now, careful, the half m's do not cancel. Okay, and they don't cancel because this operation on the top has an addition operation in it. It's got to be done first. Okay, so they cannot cancel out. Okay, that gives me VF squared. What do I want? I just want VF, so what do I have to do with everything? Square root it all. Okay, like I said, that's the trickiest algebraic manipulation that you will likely have to do in this whole course. Right there. Okay, you had to do quite a few little algebraic steps to get to this. So, when we solve this for good and plug in our numbers, it's going to look like this. Our force was 225 newtons times 10 meters minus 1/2 times 75 kilograms times 14 meters per second, okay? And that's squared. And then we divide that by 1/2 times 75. And then we square root the whole thing. Now, my suggestion here is to not try and enter this into your calculator in one step, okay? You're better to do it off in multiple steps. So we're going to have 225 times 10, okay, plus 0.5 times 75 times 14 squared. Okay, and then I'm going to divide that by 0.5 times 75. And I'm making sure to put that in brackets so it's dividing by that in total. All right, now I've got to take the square root of that. Should be 16, yeah? All right, so 16 meters per second. I know a few people got that answer, so give yourself a pat on the back. Okay, is that a reasonable answer? Absolutely. We know Usain Bolt can run it over 17. 16 meters per second is a very reasonable answer, especially considering they started at 14 and accelerated for 10 meters. That's not an unreasonable velocity for them to reach after that. Okay? All right. Questions on that one? Okay. All right. So on this one, we've got an archer who, for some reason, is shooting their bow and arrow straight up in the air. Okay, so they got it like this, they pulled it straight back, and they're going to shoot it in the air. As a real world kind of situation, what should you do immediately after launching that arrow?
Stand still.
Run.
Okay, because it's coming back. If there was like no wind and the arrow wouldn't tumble on its way back down, it would come straight back down to where it was fired from. Of course, in the real world, it's going to tumble. It's not going to be lethal by the time it comes back down. Okay, but it's not a good idea to shoot something straight up in the air because Newton discovered that whole "what goes up must come down" thing. It's been around for quite a while. Okay? So we know the mass of the arrow, okay, and we know the force that's used to pull back the bow, and we know the bow is pulled back 0.75 meters. Now we are going to assume the initial height of the arrow to be what? 0. Now obviously that's not true, because if you're holding a bow and arrow and shooting it straight up in the air, it's pretty hard to do that standing on, like, with it on the ground. Okay? We're just going to assume that that height of the person is taken into account and say HI is 0 for this one. Okay? Just in case there's any confusion there. All right, have at her. Okay, so on this one here, okay, we know the mass of the arrow. Okay, so 0.09 kilograms. Okay, so that's 90 grams. And it's fired straight up in the air from the ground. Anytime they say from the ground, it means our initial height is 0. Okay, while using 300 newtons worth of force to draw back the bow 0.75 meters. 0.75 meters. Okay, what kind of energy is being changed in this question? Potential. All right, we're comparing heights here. So we're looking at the change in potential energy. We have both force times distance, so I'm going to expand that out to force times distance. And then I'm going to say EP final minus EP initial. And what's EP initial here? 0, because we start on the ground. Okay, that means we can expand this out even more. M times G times H final. What am I looking for? H final, okay? They wanted to know what's the final height, or how high does it go? So how do I get H final by itself in this formula? Divide both sides by M times G. Okay, and so when we do that, we're going to have 300 times 0.75 meters divided by 0.09 times 9.81. Okay, so 300 times 0.75 divided by 0.09 times 9.81. Okay, so there's top divided by bottom. All right, it's going to reach a maximum height of 255 meters. That's pretty high. Okay, but I mean, you can shoot an arrow pretty far if you exert 300 newtons worth of force. That's a pretty strong person. Okay.
Say, like on the exam, if you don't round, does that matter?
You know what? On an exam, if you wrote 254.84199.8, I would be totally okay with that. Okay, we're not going to worry about significant digits in Science 10. Okay. All right, so 255 meters is our answer there for the maximum height of the arrow. Okay. Now, just so you're aware, last semester, the semester before that, and then not the semester before that because we didn't write this exam due to COVID, and then the same with the semester before that. And then before that, I had questions like this, exactly like this, on the unit exam. Okay, a bow and arrow shot straight up in the air. I put it on almost every year. Okay, I just changed the numbers. But it's a perfect example of work energy theorem. Okay, it talks force, it talks distance, it talks change in height, change in potential energy. It's just a tried and true example, so that's a good one to maybe have a look over later, and when you're preparing for your exam on May 26th.
I'm just a bit confused of why you put the triangle in the work equation.
Triangle means delta. Delta always means final minus initial. And that's what we did here, right? It's the change, work's the change in energy, so I always write it as change, and then I wrote down here what change looks like. So it's, I don't always have to write this step, because I kind of write it here with the delta. Okay? But sometimes it's easier to illustrate that when I write both. Any other questions on that one, guys? I'll get out of your way, Barrett. You were taking a picture. I don't want a photobomb. You're good. Okay. All right. Try this one. Elevator motor, 6,000 joules worth of work, lifting a 500 kilogram elevator from 14 meters to the top of a building. How tall is the building? So it's very similar to the last question, except our initial height is not what? It's not 0. So this would be as involved algebraically as a potential, question would be. It's fairly straightforward. Just like keep in mind, in this question, they actually give you the work. Okay? They don't tell you the force and distance. The reason they don't is because in this kind of problem, distance and height would be equal. So it'd be spoiling the answer by giving you the distance over which the force was exerted. So they're just telling you the work instead. Okay? All right, so in this question, they tell us that an elevator motor does 6,000 joules worth of work. They tell us the work, okay? And they tell us the mass, 500 kilogram elevator, okay? And it's going from a height of 14 meters to the top of a building. We don't know how high that building is. It's what we're being asked to calculate, okay? So we need to figure out what kind of energy is being changed here. What kind of energy is being changed? Potential, yeah, because we're changing height here, right? And elevators generally move at constant speeds. So I don't have to put in force times distance because I know what the work is, okay? And this is going to be EP final minus EP initial. Okay, now I'm looking for final height. That's going to be part of which one of those terms? EP final. So that means I need to move EP initial over to this side. So that'll be work plus the initial potential equals the final potential. Same as we did in a kinetic question a little while ago. Okay, I'm taking the change in energy, I'm adding it to the initial energy. That should give me the final energy. Okay, so still logically we're on track here. Now I can expand this out. Work, which I have the number for, plus m times g times h initial will give me the final potential energy. So m times g times hf. Right? Everybody okay with that? Okay, so now I need to get hf by itself. What do I do with m and g? Divide it over. Okay, and again, these don't cancel. There's an addition operation on the top. Okay, so now we can plug in all of our numbers. Our final height is going to be 6,000 joules plus 500 times 9.81 times 14, our initial height, divided by 500 times 9.81. Okay. So 6,000 plus 500 times 9.81 times 14 divided by 500 times 9.81. Okay, so the top of the building is not very much further. Like it was 1 meter away. Is this a question Coderre built on the fly?
Yes.
Yeah. Okay, this is a question I was rushed on and built on the fly and makes very little sense, okay, for this one. Okay, so we're going to continue working on that, guys. There's some other questions, okay, which I'm just putting in the recording here in case you want to work on them or have time to work on them, okay? But we'll be looking at them over the next little while here.
You don't